Good afternoon and welcome to, I lost count of what date this is, but this is BME 205. This is what the third last lecture before March break. While everyone makes their way into the Zoom room, I will just confirm that April 12th will be the day of the midterms.
Professor, on average, how many questions are there on the midterm?
Let me just check that day again in my calendar. Yeah, April 12th, which is a Monday, and you know I'll give you guys as long as the lecture time is to write down midterm. Well, I shouldn't say that, maybe not, but I'll give you more time than you need, I promise. I don't want to commit myself, just in case it's like a 30-minute exam and I don't want to be sitting around for 2 hours and 45 minutes. There's always at least one person that no matter what will take the maximum amount of time. And I love Zoom. They don't, but you know, again, I work very hard to make sure the time limitation is not a factor in how you do on the exams. Like historically, I always have people that leave like an hour into a 2-hour exam. And I anticipate that it will be similar for this course. I know I'm behind in posting the lectures on YouTube. I'm behind on many things in my life right now. I'll have to edit that out of the YouTube. But I am getting to it. I'm going to get to it later today. I apologize for those of you that are anxiously waiting to view the most recent lectures. The process is a little bit cumbersome because I have to, there's no way to directly upload it from Zoom. I have to download it to my computer and then upload it to YouTube. So if any of you wizards out there knows how to upload directly from Zoom into YouTube, let me know, but I don't think it's possible. Let's use bots. Yeah, I guess you could run a program. Yeah, but no, it's pretty, the YouTube uploading procedures, I don't know, maybe there's an API out there and it could be done, but there's some steps that almost require manual intervention. Let me see what else I wanted to say. I know that there was an email from the TAs to you guys about coordinating pickup of the kits. I've asked the TAs to make sure that everyone who's getting it shipped, that shipment is done this week, and everyone who's picking up, that they pick it up next week. So the goal is that everyone has their kits for spring break, so that, you know, when you're on the beach, Fort Lauderdale or Cancun or wherever you guys go, you guys can bring your circuit kits with you. Let's see. All right. We are missing some people. Could be related to the op-amps in the previous lectures. The good news is that lecture 6 is not one of the harder ones in the course. It's much more accessible. The bad news is that lecture 7 and 8 are the hardest. The hardest for me to teach and the hardest for you to learn. So let's enjoy lecture 6. We're not going to get to lecture 7 and 8 until after the spring break. We're committing three instructional days for every lecture. Right, so I'm going to cover the first third approximately of lecture 6 today, and finish lecture 6 by the end of next week, and then you're on break. With that, I will share my screen and begin talking about capacitors and inductors. So this is like a totally different, like this is a shift in the course. A shift in the course from talking about static circuit elements to dynamics. What dynamic just means changing with time. I mean, changing actually doesn't even have to be time. And so far we've looked at circuits where all the voltages and the currents, if you measure them once, you know what the value is for all of time. And so that's basically the definition of DC. But now we're going to move into AC circuits. So AC circuits involve some kind of time varying component. And capacitors and inductors introduce that behavior into the circuit. So these are elements that are capable of storing energy. And that energy is then released to the circuit at a later time. And what we're going to see is that the storage and the release of the energy is controlled by the voltages and the currents in the circuit. And with these new elements, we're going to be able to construct more useful circuits, more useful ways of processing information. So all of the techniques that we've covered so far are applicable to circuits with capacitors and inductors. So as I've said many times, KVL and KCL always hold. Ohm's law, for a resistor, always holds. And so what we're going to do in this lecture is cover first of all what a capacitor and inductor does, and how to combine them in series or in parallel. So there's very simple laws for combinations of capacitors and inductors. So lecture 6, basically you can think of it as you're going to be working with circuits that only have capacitors or only have inductors. And then in lecture 7 and 8, we're going to combine them together. So we'll look at later in the course, we'll look at circuits that have a capacitor and an inductor, or multiple capacitors and multiple inductors. For now, we're just going to deal with the basics of what these elements are. So a capacitor, as you probably know, is just a combination of two conductors separated physically with something that is an insulator, or a dielectric is another word for an insulating material. So the easiest design for a capacitor is two metal plates with some cross-sectional area A, and then some insulating material with a permittivity of, I don't know what letter this is. I don't know my Latin. I'm going to call it epsilon, but it may not be epsilon. And so that insulating layer, audience, epsilon, thank you. I was right. But there will definitely be some letters in the course that I won't get right. So two conductive plates, doesn't have to be plates, but that's kind of the textbook example of a capacitor, separated by an insulating layer. And so when you connect those to a battery, right, you get a buildup of positive charge in one plate and a buildup of negative charge on the other plate, right, as you would expect. And you get, in this picture, there is now an electric field that is formed between these two plates. And so I doubt anyone listens to the radio, anyone below the age of, I don't know, 60 listens to the radio anymore. Or maybe you do, maybe radio's coming back into fashion. But the way that a radio receiver works basically is when you tune that the dial that controls the frequency that you're listening to, you're basically changing a capacitance value, and that causes the electronic circuit to be responsive to a different frequency of electromagnetic wave. And so different stations transmit over different frequencies, and therefore by changing the capacitance, you can make the circuit respond to the desired frequency. So an example of an insulator, air, ceramic, paper, mica, I don't even know what this is, but apparently it's an insulator. And you guys know what a conductor is. And so when you connect a battery to the capacitor, you get a separation of charge. You get positive charge on one plate, negative charge on the other plate. And we're going to assume that Q coulombs of charge appear on the positive end, and you get the same but equal charge on the other end. And so the foundational definition for capacitors is here in the green box. Q equals to C times V. So the way you should think about this is if you apply 1 volt across your capacitor and you get 1 coulomb of charge separation, then your capacitance of your capacitor is 1. That never happens. With 1 volt, you will not get 1 coulomb. With 1 volt, you'll get like a micro or a millicoulomb. But so C is a property of your specific capacitor. And it controls the ratio between, in this picture, the ratio between this voltage and this charge is called the capacitance. That's all it is. So it's the ratio of the charge to the voltage that you apply to get that charge to separate. And we call a unit capacitance has 1 farad, and that's honoring the late Michael Faraday, who was a prolific physicist I guess he practiced physics in the 19th century, unless he was doing it before the age of 9. So 1 farad is a capacitor. A capacitor is rated with 1 farad if it produces 1 coulomb across the plates when applying 1 volt. So we have a nice little relationship here between the capacitance and the geometry of the parallel plate capacitor. So if the cross-sectional distance of your capacitance is A, and the separation between them is D, and the permittivity, I believe, the permittivity of the dielectric is called epsilon, then the capacitance is given as epsilon times A over D. And so the thing that you should take away from this is the following. 1, there is an intrinsic property of the insulator that influences the capacitance. So the larger the permittivity, the larger the capacitance. That's one thing. The second thing is that if you make your area larger, you get a higher capacitance, which makes sense because you have more room for charge to accumulate. On the other hand, if you increase the distance, you reduce the capacitance. And I think that also should make sense. You make the plates further apart, you need more energy to get that charge to separate. And so this equation strictly only applies to parallel plate capacitors. But again, you know, the general principles will hold to all capacitor designs. So the larger the surface area, the greater the capacitance, because you have more real estate for the charge to pile up. The smaller the spacing, the greater the capacitance, and you know, materials will differ in terms of the permittivity. So kind of like air and ceramic will have a different permittivity, for example. So capacitors have very small values. Again, pico or microfarad. The type of capacitors that you work with in the lab. I know that there may be other applications like power lines, maybe, that will have higher values, but the capacitors that we work with here are all have very small capacitance values. There's a couple of symbols. You're free to use any one that you want. I mean, in some symbols, there's just two parallel lines. There's also this one straight line, one curved line. This just means this, whenever you see an arrow through the symbol, that simply denotes that the capacitance value is tunable. So you can tune your knob. It's like in your radio receiver, you can tune your knob and you can change the capacitance. As always, we assume that a positive current enters the positive end of the voltage drop across the capacitor. And now we will get into what how to relate the voltage to the current. And so one thing that you've probably heard of, like this, the way the capacitors are taught sometimes in high school and other physics courses is you're charging up the capacitor, and then the capacitor is discharging. So basically, the way to think about it is this: when the current is constant, the capacitor is charging. And as soon as that current changes, or in the extreme case, gets turned off, then you'll see a voltage form across the capacitor. So, and that signals the beginning of the discharge of the capacitor. So when we say that the capacitor is charging, that just means that that denotes the current that's being passed through this eye here being constant. So before we get to that, there's some pictures here of different types of capacitors. So in your circuit kits, you'll get these two types here, the ceramic ones. And the ones that have the dial, those are tunable. Let's see. So these here are the variable capacitors. And they're used in radio receivers, allowing you to tune to a different station. And there are some other applications, the electromotive force, for example, noise suppression, energy storage. Okay, I don't know what's happening here, but so basically, ignore this we here. You have charge is equal to capacitance times voltage. If you take the temporal derivative of both sides, right, the temporal derivative of charge is current. The temporal derivative of a constant is a constant. And sorry, is the temporal derivative of a constant times voltage is the constant times the derivative of V. And so we have that the current through the capacitor is proportional to the change in the voltage. And so if the voltage is not changing, then there's no current flow through the capacitor. And as soon as the voltage, right, so that's you can see that by observing that when the derivative, when the slope of the voltage, when the change in the voltage is zero, there's no current. And so what I said previously was actually incorrect. What I meant to say was the capacitor is charging. When the capacitor is charging, there's no current, rather. And so the capacitor's charging is kind of synonymous with this this being constant here, right? So when the voltage is not changing, the current through the capacitor is zero. So all of this assumes linearity, and all the capacitors that we work with in this course are linear. So if we have on the horizontal axis, we have the change in the voltage, and on the vertical axis, the current flowing through the capacitor. Then we can draw a straight line that relates these two quantities. So the bigger the change in voltage, the more current will flow through the capacitor. And so this is why, it's kind of foreshadowing the rest of the course. This is really the beginning of AC circuits. So for example, if the voltage is sinusoidal, so what's the derivative of a sinusoid? See if somebody can.
A cosine.
Right. The derivative of a sine is a cosine. And so, I'm sorry, I have my phone on Do Not Disturb, but my wife, has figured out a way to have her calls be passed through the Do Not Disturb. Yes. So the cosinusoidal thing is I think that's very much a Polish thing, because that's something that my dad used to always say to me, cosinusoid, but I don't think that term is used very commonly in North America. But yeah, so the derivative of a sine is a cosine. And where I'm getting to with all this is that if you make your voltage a sinusoid, then the current will be a cosine. And so if you produce a fluctuating voltage across the capacitor somehow, then you will have another sinusoid, but now a cosine, so a different phase angle of current flowing, right? And so if V is constant, if V is just a static battery with a constant voltage, then the I is going to be zero, and there's not going to be any current flowing through the capacitor. And now we also need to be able to go the other way. So if we know the current, what is the voltage? And so if we integrate both sides of the equation, then we get the following relationship, that V is equal to 1 over C times the integral of I plus some starting voltage. So VT naught here is the initial voltage across the capacitor. So this voltage tells you that if you pass a current I, starting from time t naught to time t, the integral of that divided by C will be the amount of voltage that gets accumulated across the capacitor. So there's this term, this is how much voltage is accumulated between time t0 and t. And that gets added to whatever the starting point was. All right, so again, all we've done to go from this to this is just to integrate both sides. And you always need to have some integration limits, right? You're gonna, that current will be flowing for some finite amount of time. And if you want to start at the very beginning of time, the very beginning of the universe, then your lower integration limit will be negative infinity. And at which point the capacitor was fully discharged, meaning that the initial voltage was equal to 0. Right, so VT naught is the voltage across the capacitor at T0, the starting point. And so what it shows us, it kind of implicitly, is that the voltage at any time T depends on the past. And this is again another marker of how now we are looking at circuit elements that have memory, because the voltage at any given point in time depends not only on the current right now, it depends on what the current was previously. So that's the way memory works, like in its most fundamental sense. Memory is when some voltage, really any piece of information, depends on what happened in the past and not just what is happening right now. So we know that power is the product of voltage and current. And so if we multiply, we know the expression for current is C times the derivative of voltage. So we take that and we multiply that by the voltage. And so, the power that is stored in the capacitor is the product of the voltage and its derivative. And if we integrate that to get energy, right, because the integral of power is energy, then we get a really intuitive expression. So let's start off with that energy is the integral of power from the beginning of time to the present moment. And so we plug in this equation into the equation for power. And what do we got? We have the integral of V times dV over dt times dt. And this very nicely cancels out the dt. And so what we're left with, so what was an integral with respect to time has become an integral with respect to voltage. And so now the integral of V is just 1/2 V squared, still multiplying by the capacitance C. And what we get now is that, given that the voltage at time equals to negative infinity was 0, the energy stored at any given time t is equal to 1/2 CV squared. And if you replace V with Q over C, then you got this expression for the energy. So the energy stored at any point in time is equal to 1/2 CV squared. And this is an important relationship to understand. So what this says is that to know how much energy is being stored in the capacitor at the present moment, you have to square the present voltage, multiply by the capacitance, and divide by 2. And so that is the energy that is stored in the electric field between the plates of the capacitor. And that energy can be retrieved at some later time. And that's basically what happens when the current starts flowing in. So the voltage is constant, there's no current, and that energy is being stored in the capacitor. And then when there's a switch in the voltage, the current starts flowing, and that energy gets transferred to another part of the circuit. Okay. So one thing to note is that when the voltage is not changing, the current is 0. So what that effectively means is that the capacitor is an open circuit in DC under DC conditions. And so if your circuit is not, if there hasn't been any change in your circuit for a long time, so if it's in kind of a static condition, you can replace your capacitor with an open circuit. The capacitor only has a current flowing through it during that transient when the voltage is switching. So V hasn't changed for a long time, then the capacitor is effectively an open circuit. The other thing about it, and this is more interesting, is that the voltage cannot change abruptly. And why is that? Well, to see that, imagine trying to turn the voltage from 0 to 1 abruptly. The derivative, so, and then we're saying that the current is going to be proportional to the derivative. So this waveform here has a finite derivative at all points, but this function does not. It has a non-defined derivative at point 0 and also at this point here. So this is not, the capacitor will effectively oppose this kind of behavior. It will tend to smooth out that abrupt transition, right? Because we cannot possibly produce an infinite current. Even if that infinite current was only to be produced at a given point in time, it's not physically possible for a current across a capacitor to have an infinite value. And so the voltage across the capacitor will never actually switch instantly like this. So the capacitor effectively, it resists abrupt changes in its voltage. On the other hand, the current through a capacitor does change instantaneously, and that is exactly what happens when the capacitor goes from charging to discharging. There is an abrupt change in the current, but there is not an abrupt change in the voltage. And so we assume in this class that the capacitor doesn't dissipate any energy. It stores energy in its electric field and returns all of that energy back to the circuit. In reality, though, there is, every capacitor has a small, leakage current. So when you charge up a capacitor, some of that current will end up leaking across this resistor. But we're just going to ignore it. We're going to assume that this resistance is so high that it's not going to draw any current, and that effectively your capacitor has 100% efficiency, meaning that all of the energy that is stored across the capacitor will get put back to the circuit 100%. So there's no loss of energy when we charge and discharge the capacitor. And we assume that throughout this course. All right, some simple examples here. Calculate the charge on a 3 picofarad capacitor with 20 volts across it. So I'm going to get one of you guys to help me here. Just to save, whoops. Okay, I'll get you guys to help me with part B. So charge is equal to capacitance times voltage. So 3 picofarad is 3 times 10 to the minus 12 times 20 volts gives us 60 picocoulombs. Who can help me with part B? Who can tell me how we can find the energy stored in the capacitor? That's right. 1/2. So it's only the C is squared actually. So we'll square the voltage, but we won't square the capacitance, right? So 1/2 CV squared. So 1/2 times 3 times 10 to the minus 12 times 20 squared. And that gives us 600 picojoules. So a tiny amount of energy, as you would expect. that, a capacitor doesn't hold a lot of energy. But remember, in many cases, these voltages are just storing information. So for information storage, we don't need the values to be large for them to be usable. Okay, so that was very straightforward. Let's move on now to the practice problem, which is what is the voltage across a 3 microfarad capacitor if the charge on one plate is 0.12 millicoulombs? So what is the voltage across a 3 microfarad capacitor if the charge on one plate is 0.12 millicoulombs? We have an answer on the chat. 0.3. Oh, you already got a numerical answer. Nice. Let's find out. So it's going to be charge divided by the capacitance. So the charge here is 0.12 times 10 to the minus 3. And then we're going to divide that by the capacitance, 3 times 10 to the minus 6. Right, because if Q is equal to C times V, then V is equal to Q over C. So now we have the voltage as well. So now we need to know how much energy is stored by this capacitor. So how do we answer the second part of the question, which is how much energy is stored? So we have Q is equal to 3, 800 times 0.12. 1/2 times 40 squared. Yep. That's 0.12 times 10 to the minus 3, I think. Oh, wait a second. Yeah, let me see. So CV squared. Oh, wait, it's 1/2 CV squared. So the C here is actually 3 times 10 to the minus 6. That divided by 2 multiplied by 40 squared. So here it's going to be 2.4 millijoules. Okay. Again, there's nothing really revelational here. It's just putting numbers into these canonical equations. All right, something that requires a little bit more thought, potentially. We're given the voltage of 10 times cos 6,000 T. And we're told that our capacitor has a value of 5 microfarads. We are asked to calculate the current, right? So remember, to get the current, you have to integrate the voltage and divide by the capacitance. Right, so I'll work through this one. Oh, whoops, what am I saying? It says get the current, you have to I'm not on my game today, I'm sorry. To get the current, you have to differentiate the voltage and multiply by the capacitance. And so our capacitance is 5 times 10 to the minus 6, and we have to differentiate this cosine, right? So to differentiate this cosine, you would use the chain rule. And the chain rule is that the constant 10 stays, and the derivative of a cosine is a sine, and then we have to differentiate the argument as well. So the derivative of 6,000 T is 6,000. And the minus sign is because the derivative of a cosine is a minus sign. Right? And so the current here is equal to negative 0.3 sine 6,000 T. So this will become apparent throughout the course, is that if the voltage is a cosine, the current is a sine. And if the voltage is a sine, the current will be a cosine. All right, so you'll often see this, and it will be the opposite for an inductor. And so, does anyone know what the phase angle is between a sine and a cosine? What is the phase difference between the sine in degrees, let's say? 90, exactly, right? So in other words, the voltage and the current are always 90 degrees apart. Alrighty. So more practice problems. We have a 10 microfarad capacitor connected to a voltage source with a value of 50 sine 2000 t. And we are asked to determine the current through the capacitor. So how do I approach this? How do I approach the problem of solving for the current? Differentiate B. So what's the derivative of 50 sine 2000 t?
50 times
A is a constant.
2000 cosine 2000 t.
Oh my God, I just realized something. I hope you guys haven't been talking. Give me a second here. Just realized that my sound is going through my headphones. Hold on. Let me, how do I get to the Zoom menu? Oh, Jesus. It's weird because when you go here, it shows that I'm connected to my speakers. Okay. I hope you guys haven't been talking and I just haven't been hearing the whole time. First of all, can you guys hear me? You can just say something on the chat or say yes. Okay, good. I apologize for that. Thank you. I thought, I was wondering why nobody laughed at my jokes. Okay. No, thanks.
Can you hear us now, Professor?
Yeah, I can hear you. I'm so sorry. It took, I guess, Omar, I think you have a nice loud voice and I heard it coming through my, headphones, which were kind of next to me. Okay, so we're going to differentiate the voltage, which is going to be 50 times cosine 2000 t times 2000 and multiply by the capacitance to get the current. Right. And then the product of these coefficients works out to be 1. And so again, we see that when the voltage is a sine wave, the current is also a sine wave. And this brings me to a part of the course that I always ask, actually. So maybe what I'll do is just add a next slide. Here's a question. So what is the frequency of sine 2 pi 100t? So let's back up. What is the period of sine x? What is the period of a sine wave?
2 pi.
2 pi, thank you, 2 pi. What is the period of sine, let's say, a times x?
2A pi.
2a pi is very close.
Two
2 pi over a,
over A.
right? Exactly. So now, given that, what is the period of sine 2 pi times 100 times t?
100 times T. Oh, wait, no.
2 pi.
2 pi over 100 times T.
2 pi over what? 2
100.
pi. 2 pi over 2 pi times 100, right? Which is equal to 1 over 100. Meaning that the frequency equals 100 hertz, right? This is seconds. This is, I don't know how, I'm not going to write the superscript, but it's, right. So the frequency of this sinusoid is 100 hertz. So I always wonder, this confused me. Why do they write it like this? Why do they write everything multiplied by 2 pi? Well, that's just an easier way to denote the frequency, right? And so if you often see in these problems that the sine wave is written as a product, as a something multiplied by 2 pi. Well, that's just an easier way of denoting the frequency of the sine wave. Where was I? Here. I can delete this slide now. So we're gonna go back to this, right? So we have a 10, oh no, we did this one, sorry. Moving on to this one. So here's the problem that I was thinking about, where we're given a current and we are asked to solve for the voltage, right? So we're given the capacitance, 2 microfarads, and we're given the current. And so here's where we have to integrate the I divided by the C and then add it to the initial voltage, which is given to us as 0, right? So we need to integrate this function. So how do what's the integral of an exponential?
Is it 6 times e to the negative 3000 over negative 3000?
Yeah, exactly. By the way, there's something do you guys know what's special about this function? What is special about this function? But it's the only function that I can think of that has one very
The
important
derivative
property.
is equal to itself.
Yeah, exactly. That's super useful for I mean, it's the basis of the Fourier transform and other tools in engineering. So it's like an eigenfunction. It's a function which, when you differentiate, you just get it back, which is interesting if you think about it. So the slope of the function at any point in time is equal to the value of that function. And so the reason that function, it just makes a lot of kind of engineering analysis simpler to do because of that property. And so, yeah, what Christian, when he said was right, you just, to integrate this, you express it, you just write the derivative as e to the minus 3000 t over negative 3000. And so there's a couple of things here that are kind of that be confusing, but shouldn't be. This 10 to the minus 3 is put in here because it's milliamps, right? So I don't like the way it's written after the dt, but you could have put that in the front. And then to go from this step to this step, all that has happened is the negative 3,000 has been put to the denominator, and the 2 times 10 to the 6th has been put to the numerator, and then the 10 to the minus 3 has been also absorbed by the numerator. And so there's 3 things happening here. From this step to this step, the negative 3,000 and that's the integral of this has a negative 1 over 3,000. We move this to the numerator with a positive exponent, and then we multiply that by 10 to the minus 3. So it's just a lot of ugly math, but at the end, what we get is a function whose value is 1 minus e to the minus 3,000 t volts. So my question to you is this, and I always ask this question because I find it's a good, I like to look at the extreme cases. So when t is equal to infinity, what happens to this function? Yeah, that was quick, man. Yeah, that's right. It becomes 1. Because when t is equal to infinity, this becomes e to the minus infinity, which is 1 over e to the infinity, which is 0. Now, what about the case when t is equal to 0? What happens to this? What happens to this voltage when t is equal to 0?
0.
That's right. It goes to 0, right? So it starts off at 0 and goes to 1. Right? So if you look at the time course, right? The time course, undo that. This is the time axis, right? So we know that at 0, it starts off at 0. And at infinity, it goes to 1, the voltage. And so in between there, generally you'll see, oh, there goes my cursor. It didn't take long. Hey, this is a brand new computer. And it still has this problem. This is unacceptable here. No, like it's a meeting. See if I get it back. Yeah, so it goes something like that. Right. And the way you see that is if you have a constant function of 1 and you subtract from it an exponential. So this minus this, it doesn't quite work actually. Let me see. Or does it work? I was gonna say that this is the result of subtracting an exponential from a constant, but I'm not sure if that's actually true. This shape actually looks more like an inverted exponential, but it should be. Let me see, 1 minus. I guess that's right. Oh, yeah, that's right. Yeah. If you subtract this from this, you do get this. And so but what I'm trying to say is that this voltage starts out at 0 and plateaus at a value of 1 volt. All right. Moving right along. I mean, not really. It's not really an AC circuit. You'll get that when AC circuits really mean you have sinusoids for the sources. So you have a sinusoidal, so you have a battery who's that's pumping out a sinusoidal voltage. but this is the precursor. This is the prequel to AC circuits. All right, clear. We have another one is from the current through a 100 microfarad capacitor is given by 50 sine 120 pi t. Yes, yeah, but we're not at AC circuits yet. But yeah, a sinusoidal voltage will be constantly going back and forth. Well, it won't be going between two values. It will be alternating between positive and negative, but it has a smooth, it has a sinusoidal shape. So it's a smooth transition. 50 sine 120 pi t is the current. So what is the, now I can ask this question. What is the frequency here of this current? We have an audience answer, 60, excellent, well done. 60 hertz is the frequency of this current. And that, by the way, is the frequency of AC transmission in North America. I'm not sure if it is in Europe. It may actually be 50 in Europe. But I know in North America, it's 60 hertz. We are asked to calculate the voltage across it at 1 millisecond and 5 milliseconds, assuming that the initial voltage is 0. Okay, so what do I do with that current to get it into a voltage?
Integrate it and multiply it by 1 over the capacitance.
Yes. And so what is the integral of this waveform? It's going to be cosine 120 pi t, that's right. 1 over 120, I think that looks right. So again, because this milliamperes, we stick in a 1 over 1000. And that's going to get moved out to the front, as is the 50. And then the integral of a the integral of a sine is a minus cos. So we have all these numbers here that we can condense into 500 over 120 pi. And then that gets, so the 1 minus cos 120 pi t is the result of evaluating this at t minus, okay, so there's a couple of things. This minus 1 here, actually, let me just write it out. Right, so if we have minus 1 times, I love my kindergarten handwriting on Zoom. This is what kids feel like when they're learning how to write, I bet. So this equals to cos 0 minus pi t, right? And this is equal to 1, right? So this term here is just that, and then that cancels out the minus 1 here. And so 50 over 100 is a half. And then a half times a million over 1000 is 500, and then the 120 pi stays. So if the reason that the frequency of this is 60 is that we said previously that the frequency of sine 2 pi f, the frequency of this is f hertz. And so in this question, 120 pi t is equal to 2 times pi times 60 times t. And so the frequency of this current is equal to 60 hertz. Okay, does anybody have questions? Or sorry, we're not done yet. We actually have to evaluate this at 1 millisecond and at 5 milliseconds. So we just plug in 0.001 for t and then 0.005 for t. And that gives us values of 0.093 volts at 1 millisecond and 1.73 volts at 5 milliseconds. Okay. Does anybody have questions on this problem or any of the other stuff that we've covered so far today? Okay. I'll take your silence as 100% incontrovertible comprehension. Not even sure if that's the word. Oh, I like this one. Determine the current through a 200 microfarad capacitor whose voltage is shown in A. So first of all, before you do the math, what is the current across the what is the current across? This is a super sensitive touchpad on this new Mac. But I'm not happy with it, to be honest. There's some flaws. 50. So it's actually going to be time varying, right? So what is the shape? So this is the voltage. What across a capacitor? And we are asked to determine the current through that capacitor. What is the waveform of the corresponding current going to look like? What kind of a waveform is it going to have? It's going to be a sinusoid. Is it going to be a sine wave? Nope. But I'm happy
It's
to
just
do
gonna
that.
be like a straight line.
A straight line. That's a partially no, but it's still not. It's not going to be a straight line, right? Because the derivative is not constant everywhere. It's only constant along sections of this function. Right, so the derivative of this function, I'll try to, this is a good opportunity actually to draw.
Is it
over
zero?
this. No, it won't
This
be
is gonna be
zero.
like skipping, like straight lines, but like up and down.
Yes, it's going to be a square wave. It's going to look like this. Because the derivative is alternating between a slope of 50 and negative 50. All right. So now let's actually do the math. That was just like, it's always good to have the intuition in your head. And then let the math kind of confirm your intuition. Yeah, the square wave is the derivative of this sawtooth wave, I think it's called. Okay, so let's differentiate. So first of all, let's write this function in piecewise terms. So this first section here is just 50 times t. The second section here is 100 minus 50t. And this third section here is negative 200 plus 50t. So y equals mx plus b. I think we all remember that from high school. For some of us, it was many moons ago. For you young bucks, it was just a couple years ago. And now let's take the derivative of each of these terms and multiply it by C, right? So C here is equal to 200 times 10 to the minus 6. And then the derivative of this is 50. The derivative of this is minus 50. The derivative of this is 50. So that gives us our square wave, which you work with a lot in electronics. Square waves are very common. It's just many waveforms they use in practice. For example, for ultrasound applications, you often put out square waves out of the transducer. It's a very common shape.
I think you guys will work with this in the lab section, if I remember correctly.
Nice. Yeah, make them. Sam and Tariq are gonna ask you guys to put out some square waves. All right, practice problem. An initially uncharged, that means that the initial voltage is 0. 1 millifarad capacitor has the current shown in the figure. So the current goes from 0 amps, 0 milliamps to 100 microamps in 2 milliseconds. Calculate the voltage across it at t equals 2 milliseconds and t equals 5 milliseconds. So at this point, and then also at this point. So first of all, before we get into the math, what do I have to do to this function to get the voltage?
Area under 2 to 5.
Yes. Yeah, area under the curve from 0 to 2, and then from 0 to 5. Right? Because it's calculated the voltage at 2 milliseconds and at 5 milliseconds. Between 2 and 5 would be if the question was calculate the voltage that accumulated between 2 and 5. So that's just a little bit of wording there that may be confusing. Yeah, so we have to find area under the curve. So first between 0 and 2, and then between 0 and 5. Or we can do it in 2 steps. First 0 and 2, and then between 2 and 5. That may actually be easier. Okay, so here's our fundamental equation. The voltage is the integral of the current divided by the capacitance. So let's, oops, again, so sensitive. Well, guess I'll just do the first part since I've already shown it to you. We have to integrate the function, which is equal to 50t. So how did I get this 50 here?
100 divided by 2.
That's right. That's the slope. The slope of this line is 50. Remember, so it's 100 microamps per 2 milliseconds. So the slope is equal to 50 amps per second. So you can think of this as being in units of amps per second or milliamps per millisecond. And we have to integrate that between 0 and 0.002. And then we have to divide it by 1 milli or 0.001. And the integration is going to be between 0 and 2 milliseconds, which is 0.002. Right, so the integral of t is t squared over 2. So 50 over 1 times 10 to the minus 3. So 50 over 1 times 10 to the minus 3 times t squared over 2, and the t squared over 2 has to be evaluated at 0.002, and then minus t squared evaluated 0, which is just equal to 0. So basically, we just plug in 0.002 into t, square it, evaluate, and you get 100 millivolts. So that is the voltage at 2 milliseconds. So now we want to know the voltage at 5 milliseconds. So what should my next step be?
From that value, you can add on the area under the curve from 2 to 5.
That's right. And so what is the function going to look like that I'm integrating? So here the function was 50t. What's the function going to be in the next integral?
Constant 100.
Constant 100 is, yeah, it's actually 0.1, yeah, because it's a milliamps. So 100, this is tricky, right? Because it's milliamps, and so when you're integrating, you have to do it in amps. Always
But for
convert
the other
this.
one, you put 50.
Yeah, I know, because it's here, this, and this is the tricky part. This is milliamps per milliseconds. Right,
Oh,
hence,
okay. Cancels out.
right,
Okay.
so it's effectively amps per second here.
This is
So,
constant over milli.
yeah. Yeah, I mean, you could just do all of the math in units of milliseconds. I don't know, maybe, but for me, that's just, I'd rather just switch everything into standard units and perform the computation there. But it's not difficult to see that the integral, the area between 2 and 5 is just, it's a rectangle, so it's 100, so it's 0.1 evaluated over an area of 0.003. And so we're going to tack on whatever the voltage was at 2 milliseconds. That's this term here. So this here is just a repeat of this, which we already know is 100 millivolts. That's over here. And so this is this here is the area under the curve between 2 milliseconds and 5 milliseconds. So the integral of a constant is just the integral of 0.1 is just t, and then t gets evaluated between 0.005 minus 0.002. That gives us the 0.003. So again, the math here is a little bit messy or confusing, but it's really just straight up some very simple calculus here. And this term here ends up working out to 0.3 volts. And so the answer is 400 millivolts. Does anybody have questions as to how we got to both of these solutions here? Why did I take the slope? I took the slope because I wanted to write, I needed to express this function, this current as a function of time. So the equation for this function is 50 times t, because the slope of this line is 50 and the y-intercept is 0. Why is my screen sharing paused? So weird. Can you guys hear me?
Yeah,
Okay, good. Sorry, yeah, so I took the slope. I needed to write this function. I needed to write this line as a mathematical function that I could integrate. And so the slope is 100 mil. If you write this in amps, it's 0.1 divided by, sorry, yeah, 0.1 divided by 0.002, which is 50t. So 50t is the equation of this line, which I have to integrate. All right, last two slides here before we adjourn for the day. We have to obtain the energy stored in the in each capacitor in this circuit under DC conditions. So remember what I said, under DC conditions, a capacitor acts like an open circuit. So we can assume that the 4 millifarad capacitor is an open circuit and the 2 millifarad capacitor is an open circuit. So how do we go about determining the voltage across this capacitor and across this capacitor? So I need this voltage here between, and I need this voltage here. Any ideas? How would I redraw this circuit with those capacitors open circuited?
There would just be an open in that
Yeah.
area.
So what does that, yeah, so what does that do to the circuit? Let me see if I can. Right. So this 5K resistor is effectively ignored. And so now in this picture, how much of the 6 milliampere current is going to flow here? So the current that comes out of this battery can either go down and take the 3 kilo ohm, or it can go around and take the 6 kilo ohm. Yeah, current division, right? So the current I here is equal to 6 times 3 over 3 plus 6, right? There's 6 ohms, 6 kilo ohms in this branch and 3 kilo ohms in this branch. So this branch will get 1/3 of the original 6, right? Because it has 2/3 of the resistance. So 2 milliamps flows this way. And so if 2 milliamps flowing along this way, what is the voltage across a 2 kilo ohm resistor? Four volts, exactly. 2 milliamps times 2 kilo ohms, right? So that means that V1 is equal to 4 volts. And now I got here that V2 is equal to 8 volts. So how did I get that? How did I go from that I is equal to 2 milliamps to V2 is equal to 8 volts? Notice that this node here, this 5 kilo ohm resistor is dead. And so this node extends to here. And so in other words, V2 is in fact parallel to the 4 kilo ohm resistor. And that 4 kilo ohm resistor has a voltage drop of 4 times 2 or 8 volts. Right, so notice this V2, because this 5 kilo ohm resistor doesn't draw any current, it's effectively just a piece of wire. And so V2 is in fact parallel to this 4 kilo ohm resistor, which has a current of 2 milliamps and a voltage drop of 8 volts. And so to get the energies, we just take the voltages, square them, multiply them by the capacitance, and divide them by 2. So I think we all know how to convert from a voltage to an energy. The hardest part is just redrawing the circuit and then realizing that V2 is in fact the voltage across the 4 kilo ohm resistor. Any questions on this problem?
So how exactly is the 5 kilo ohm resistor dead?
Yeah, it's dead because there has to be a complete path for any current that flows through here does not have a way to return to it, let's say, to return to the positive end, right? This is an open circuit. So this is just the current has to flow in loops. So there's no loop that takes you through the 5 kilo ohm resistor in the circuit, if that makes sense.
The current goes to that capacitor and it charges up, And if the current source were to change or turn off, then it would flow out the negative side, would release from the capacitor.
Yeah, so that's a really good question. Yeah, exactly. Now, we are doing this analysis under the assumption that that current source has just been on for a very long time and nothing's changed. But as soon as that, let's say that current source was to switch off, then the current flow, I mean, it depends on what, if V2 is positive, then the current would come out of the positive end and go around like this. Right. Then the positive charge would flow out like this, and it would go through the 5 kilo ohm resistor. But that's not under DC conditions. That's only on the assumption that you switch off this current source, for example. But yeah, everything that I've said is only true for DC conditions, which mean not the circuit has been sitting there without any change to the sources. All right, one more problem and then we will adjourn. So find the energy stored in these capacitors, right? So let's redraw. Could you go back? Yes, sure. What is your question? Oh, the capacitance is given to us. 2 millifarads, 4 millifarads. Yeah, it's always going to be given to you. There's not a question in this course that you have to find the capacitance. It will always be given to you. Under DC conditions, find the energy stored in these two capacitors. So what is the circuit going to look like under DC conditions? How many loops are there going to be in this circuit under DC conditions?
Wouldn't there be one loop?
That's right. Very good. There is just one loop. Right. So the current is just going to go like this. So how much total resistance is in this circuit?
10 kilo.
10 kilo ohms, which means that how much current is flowing? There's 10 volts and 10 kilo ohms. That means that there is 1 milliamp. Thank you. 1 milliamps. And so that means that the voltage drop, and I did this with the voltage division, but you can do Ohm's law. So we get, if you divide the 10 volts by the 10 kilo ohms, you get a current of 1 milliamp. And so the voltage drop across the first resistor is a volt. The voltage drop across the second resistor is 3 volts. And the voltage drop across the third resistor is 6 volts. I want to try to. So what is the voltage across the 20 microfarad capacitor here?
3 volts.
3 volts. That's right. But what about the voltage drop across this capacitor here? What's the voltage between this point and this point? Six. Nope. But it's a good guess. 9 volts is correct. So how did I get the 9 volts? Well, you can just apply KVL. Like there's two ways of looking at it. The voltage from this point to this point is the same as this voltage here that I'm tracing, right? And so the voltage drop from here to here is 3, and the voltage drop from here to here is 6. So I have 3 plus 6 will give you 9. Another way is just to do KCL, and if you call this, say VC for capacitor, we have negative 10 plus B1 plus BC equals to 0. And then VC is equal to 10 minus V1. All right. And what's going to be the energy stored in the capacitor? Who can tell me the energy stored in the capacitor? Much harder to do this over Zoom. That didn't quite work out the way I wanted. Shout out to Draw So Cute, whose videos helped me when my daughter was much younger than she is now. Who can tell me the, it looks much better when I draw it on paper. 405, excellent. Exactly. 180 for the other. Let's take a look. So it's going to be, remember, it's 1/2 CV squared. So 1/2 times 20 times 10 to the minus 6 times 9 times 3 squared, right? Which is equal to 405 microjoules, right? 1/2 times, oh wait, I'm doing this one, sorry, first. So 1/2 times 10 to the minus 6 times 9 squared is 405 microjoules, 405 microjoules. And why is not, oh, I know why. So the voltage across here was 3 volts. So the energy stored by the 20 microfarad capacitor is 1/2 times 20 times 10 to the minus 6 times 3 squared, which is 90 microjoules. So again, very small amounts. All right, is there any questions about anything that we covered in today's lecture? Okay, with that, I wish you all a good weekend. I will post the 3rd homework assignment imminently. I believe it's going to be on Norton and Thevenin. So there'll be an announcement on the Blackboard for that. Midterm is April 12th. Please send Sam and Tariq your shipping information if you haven't already done so, or tell them the date during which you will pick up your circuit kit. I want us to all have the month of April to do the labs. And I will see you all next Monday.
Homework due tonight. Don't forget it.
Yeah. Thank you for the reminder, Sam. 11:59 Eastern Standard Time. I'm sorry for those of you in the Hawaii time zone.
Also, like if you want me to review your homework, like you can just submit it on Blackboard and send me an email or on Slack, and I will go over your homework to see how you're doing and to let you know if you need to redo some questions. Yeah.
Thank you, Sam. Bye, guys.